lecture line 19, limit and continuity. So you've done the limit continuity part, right? You're done in your +2. So I'll start from an example. You know this example, right? How to calculate this. Okay. So you know?
Yes, sir.
Yes, sir.
What was the idea? That's how?
Yes,
And
sir.
this will come out to be 4, right?
Yes, sir.
Yes, sir.
No, why we moved this to this and then this to this?
ताकि नीचे डिनोमिनेटर 0 ना हो.
Okay, so what does that actually mean? X approaches 2.
Sir, actually,
कम कर रहे हैं हम.
Sir, actually, sir, we are removing the 0 by 0 form.
Yes, sir.
Yeah, true. And then?
सर हम ये कह सकते हैं उस पॉइंट पे एग्जैक्टली डिफाइंड नहीं है वैल्यू, इसलिए उसको अप्रोच कर रहे हैं.
Yes.
इसलिए लिमिट यूज कर रहे हैं.
Yes. So that means X is very near to 2. Right? But X is not equal to 2. Is it fine?
Yes, sir.
But still these terms are very vague. How much near? We don't know. So let's say we take an example. If you take X to be 1.9, so this function will become what? 1.9 square minus 4 upon 1.9 minus 2. Right? So this becomes 3.81 minus 4 upon minus 0.1. So that becomes what? क्या बनेगा जी?
90.
सॉरी यहाँ गड़बड़ कर दिया कुछ. ये कितना बन जाएगा? हाँ, तो ये बन जाएगा. We'll have 3.9 over here.
3.9. Yes, sir.
So if you take 1.99.99, if you take 1.999, it becomes 3.999, right? Similarly, if you put X to be 2.1, your function at 2.1 will give you the value 4.1. And this as compared to, so the resulting value will also be closer to 4.01. If you take more close value, again the result will be more close to 4. So this is the example I guess most of you have already done. Have you done that example in this way, right?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Right. So we basically call it as, in your terms, we call it as left hand limit and right hand limit, right? So this is your X is equal to 2. If you take the right,
Sir, your voice is
आवाज
lacking.
clear नहीं आ रही.
So you are lacking, sir.
जाम कर.
सर
okay,
आवाज
okay.
नहीं आ रही.
Just a minute. एक मिनट रुको. अब आ रही है आवाज?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir. Now you are audible.
हाँ, तो अभी देखो जरा. तो let me plot this thing for you. So if you take it as x minus 2, x plus 2, x minus 2, and you cancel it out, and you put, so this is a kind of straight line, x plus 2, right? So if you put x is equal to 0, y will become 2, and if your x is equal to, if your y is 0, x becomes minus 2. So in this way, this is the plot, right? And with this point as exception. Okay, so this point is an exception. Why? Because at x is equal to this thing is not defined, right? Is it okay? So this is the plot of
Yes,
this function.
Yes, sir.
Are you getting this? Right. So
Yes, sir.
if except
sir.
this point, everything is fine, then everything will look like just a straight line. Okay, this straight line. Right?
Yes, sir.
Are you getting this?
Yes, sir.
Yes, sir.
Are you with me on
Sir.
this? So
Yes, sir.
that generally you've done the things in like left hand limit and in the format of left hand limit and right hand limit. So what do you say? Ki left hand limit at x is equal to 2 must be equal to the right hand
limit.
limit x is equal to 2. Okay. Is it fine?
Yes, sir. Yes, sir.
So are you with me on this?
Yes, sir.
Yes, sir.
ठीक है.
एक बार लास्ट स्लाइड
So now see this. कौन सा last point?
लास्ट स्लाइड एक बार ही करना
Sir,
ये last पे ही होगा.
Bhanu Rakshita got disconnected mistakenly. Can you please let her in?
Can you see the screen now?
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So is it fine now?
Yes, sir.
Yes, sir.
Sir.
Yeah, this is the last slide. If somebody wants to ask something, is it okay?
Yes, sir.
Okay, sir.
Okay. So, there were few vague things. That was how near, approaches, how much. These all words were vague, right? In order to get a concrete definition into that, so what we say that as x approaches, let's say a, if we are taking the limit at a, then f of x. So essentially this means that as x approaches to a, f of x approaches to L, that means that your x and the difference of your x and a is very small, and difference of fx and L is very small, right? But these two very small and very small cannot be equal, right? Because you have mapped x through f, so now here you have different numbers, so you cannot expect every time that the difference of x and a and difference of f of x and L can be the same, right? So that's how the epsilon delta definition will come into the picture, and we'll do that more rigorous definition. We call it as epsilon delta definition of limit. Right, so try to understand this definition. I'll keep it as simple as possible. So let f of x be a function defined on an open interval about x is equal to a, and let limit x approaches to a, f of x is equal to, let's say, capital L. An alternative definition of epsilon delta, that's what, for every epsilon positive, for every epsilon positive, there exists a delta positive such that whenever this thing happens, this should imply the difference of fx and L will be less than epsilon, right? So this epsilon needs to be as small as possible. So that we'll discuss. That's why. So basically, all of you who have heard about the epsilon delta definition in sequences, epsilon used to be a challenger and delta used to be a defender, and the same wording will be using over here. So our epsilon will be a challenger and our delta will be a defender. So I'll put it as this is challenger and defender. A space issue anyways. So let us understand this thing with the help of graph, that then you will come to understand that how this definition will work for us. So basically what? So let's say you have a very nice function. Let's say I draw a very nice function for you, and that's it. And you know that this is a function which is continuous, and of course at this point limit will definitely exist. So at this point, let's say this point is a, and you know that your limit is exactly going to be the functional value, right? So this is your, let's say, L, right? And this is at x is equal to a, and this is your f of x, because this function is pretty much nice. Now what happens that if you draw a line around this point, so let's say you put a challenge over here and you draw lines around this L. So let's say these are the two lines, right? So now if you take an interval, corresponding interval, let's say this and this, you will come to know that if even this, yes, this and this, you'll come to know that all the values between this delta and here delta, these are the epsilon lines, right? So this is a kind of line which is of L plus epsilon, and this is L minus epsilon. So no matter how much value do you take from a minus delta to a plus delta, the value of function, so these are the values of function, right? So these are the inputs in the interval a minus delta to a plus delta. So this is your interval a minus delta to a plus delta. So you pick any value over here, you will come to know that this value will get mapped over here, and all these values are actually between L plus epsilon to L minus epsilon to L plus epsilon, right? So every value will get mapped over here, and that's what we have said over here, that it doesn't matter, you pick however the small epsilon is, here you will get a delta over here such that these values will get mapped to these values. These values, when we map them, they will definitely satisfy this inequality. That means fx minus L is less than epsilon. Now if you see this inequality, so let me make it clear over here that if you pick this inequality, you talk about this inequality. So when you solve this inequality, this will be like a minus delta to a union a to a plus delta. That means, in other words, that is a minus delta to a plus delta except point A. So you discarded the point A. Why? Because generally when you are talking about the limit at certain point, then that point may or may not be the part of the domain. For example, when you talk about this, right? So here 2 is not in the domain of this function. Why? Because if you put directly 2, then it will become 0 by 0 form. So 2 is not in the domain, but you can always find the limiting value, right? So 2 may not be the part of the domain, and that's how, the limit problem comes into the picture, because 2 is not in the domain of the function. So that's why we are talking about the limit. So that's why this 0 is over here. This 0 ensures that this a point may not belong to the domain. However, if function is continuous, then certainly a will be in the domain of the function, and the limiting value will be equal to the functional value. That means your limit x goes to a, f of x is equal to f of a, that you know, right? But when you talk only about limits, then that a may not be in the domain of the function, as you see in this. Now, there are certain scenarios where when this thing will not hold, right? Let's say talk about those scenarios when these values will not get mapped. Okay, so there may be a very simple scenarios as well, there may be a very bad scenario. So let me pick a scenario for you. Let's talk about our previous function and we'll try to draw this, try to draw a picture for this and try to understand this example with the help of epsilon and delta. So if you draw, let me draw it on next page. So let's we draw it. Okay, so as we have discussed, this is nothing but a straight line, except at x is equal to 2, this function is not defined, right? Otherwise it's a straight line, y is equal to x plus 2, right? So if it is y is equal to x plus 2, then if you put x is equal to 0, so y will be 2, and if you put y is equal to 0, then x will be of minus 2. So let's draw a straight line, but at x is equal to 2, of course it is not defined. So let me make a graph of this function. Okay, better, right? So this is a kind of the functions graph, but we know that at this point the value is not defined. So let me make a break over here. Okay, so now we know that the limit of the function is 4 over here, right? We usually solve it like this, as we have done. This is 4. So in this case your L is 4, right? So this is your L over here. So let me draw. So this is 4. Now it doesn't matter how much big or small epsilon you take around this, and you will definitely get a limit. You will definitely get those deltas, so that every value will map in that box and will remain in that box. Let's how it works. So let's first of all you make a choice of bigger epsilon, right? So let's say you kind of make this epsilon over here, okay, and then you have a corresponding deltas over here. Okay, so let me complete the box for you, just like this, and just a minute. Yes, so these are the, let's say you can choose such a delta over here. So let me complete the picture for you, this, and from here it is this. So now if you see that, if you take an epsilon over here, so that is your 4 minus 4 plus epsilon, and that is your 4 minus epsilon. So that much epsilon you have taken. So now you know that, so around x is equal to 2, you have delta, so that 2 minus delta to 2 plus delta, so that you pick any value over here, it will get mapped over here, and these all are what? These functional values will get mapped over here, of course on the y-axis. All those values are lying between 4 minus epsilon to 4 plus epsilon, right? So whenever your x belongs to 2 minus delta union, 2 minus delta to 2 plus delta except 2, so all your values, all your f of x belongs to 4 minus epsilon to 4 plus epsilon. So that's why this function is nice to us, and we are getting the L to be 4. Now we shall discuss the case when the limit does not exist. So we'll understand this case graphically and definitely with the help of epsilon delta definition. So let me make the graph of a step function where we know that the limit does not exist. So let's say this is the step function, and this is the point at which we want to check the limit. So this is the point, we may call it as x is equal to a. You assume that L is somewhere limit of this function at x is equal to a, which is not, but we'll prove that how it is not. So let's say we draw a line and we draw a horizontal line, something like this, or more precisely like this. So now I'll make 2 copies of that in order to understand it completely. So I take the copy of this graph over here. So first of all, if you try to take a bigger epsilon and if you try to make a bigger box, then you may have an impression that this limit exists, but which is actually not so. So let me take these examples first. So if you take a lines, let me draw pink lines with bigger epsilon here and here. So this is epsilon apart from L, so we call it as L minus epsilon to L plus epsilon. Now you take any delta around x is equal to A. So no matter if you take a bigger delta or a smaller delta, let's say you take this delta and this much. So now if you see the box, if you mark your box carefully, so let me choose the color of the box, something like this. So this is your box. So in your box, if you see those values, then you will feel that your values are actually mapped into the box. So which is actually the case is. So if you take those values here, right? So this is your A minus delta to A plus delta. So, and you see those values, every value is mapping in the box, right? So every value is in the box. And if you see the corresponding values on the y-axis, of course, they are actually lying between L minus epsilon to L plus epsilon. But this may not hold for every box. That means our smaller epsilon is actually the challenge. Take the smaller epsilon, you will come to know that this limit actually does not exist. So take the same picture and see the second part. If I choose and I'll take the red color and I choose a smaller epsilon around this L and I'll draw the lines, horizontal lines, this and this. Now these are the lines of your L minus epsilon to L plus epsilon. I've chosen a comparatively very small epsilon. Now no matter which delta you choose around your x is equal to A, that means here to here. So this line and this line. Now mark your box carefully. So if you see your box again, in this case, this is your box, right? And if you see those values again, so your values in A minus delta to A plus delta, this is your A minus delta, this is your A plus delta. So every value is mapping here or here, right? So if you see the corresponding values are mapping here or here, so of course these two values are outside the L minus epsilon to L plus epsilon. So this is the idea which we want to discuss over here, that there are many values which are actually lying outside the box. And there may be the case when you say that there are few values which may not lie in the box and few values may lie in the box, but we want every value of this interval lying in exactly mapped in this L minus epsilon to L plus epsilon. Even if one value is missing, we'll say that limit does not exist. And here we have one such bad epsilon for which these values are not mapping in the L minus epsilon to L plus epsilon range. So now we shall discuss the case when limit does not exist. So that means precisely we'll write the case when we'll write the negation of this statement. So this statement says that, read carefully, this statement says what? For every epsilon there exists a delta so that every value will get mapped. So that every value will get mapped in the epsilon range of L. So the negation would be, for every, the negation would be there exists some, there exists one. So there exists one such epsilon for which all the values will not map over here. So let's see how we write the negation of this statement. We take the negation of that, that means there exists one epsilon which will not hold. For one epsilon, this condition will not hold. So when limit does not exist, how we write the proper definition of that? So we say that limit x goes to a, so limit x goes to f of x is not equal to L when, by providing one such epsilon, right? One such bad epsilon, right? This will be bad such that there is no such delta positive. Positive is already there. There is no such delta positive which satisfies that for all x belongs to a minus delta to a plus delta except a should imply f of x minus L is less than epsilon. That means in that case all those values will not obey this law. So that means there exists some bad x naught, right, which belongs to this interval, but does not satisfy f of x minus L less than epsilon, right? So in other words we can say that we rewrite this as there exists some x naught belongs to a minus delta to a plus delta except a, right, such that f of x naught minus L ka mod is not less than epsilon. So when it is not less than epsilon, what does that mean? So that means that it has to be greater than or equal to the epsilon. So you can draw one more picture where you can, where you can again, map those ideas. It's not only about the step function, it may be any other function which is misbehaving, right? And that's what. So let's say you have this and here, so if your function breaks, of course this will not make sense when we'll calculate the limit, right? So let me put it in that way. Even if you take the limit over here, even then it will not work, right? If you say that this is the limit, right, and then you take L minus epsilon over here and L plus epsilon over here, sorry, L minus epsilon over here, L minus epsilon over here, L plus epsilon over here, L and L over here, even then there will not be any box you say, so that the values will get mapped over here. So if you take this box, let's say for an example, so this is your, at this point, let's say you are talking about the limit x is equal to a, right? And let me make it more clear. So let's say over here, yes, over here. So now you make any box around this point, so your value will not get mapped into that box. You can see it clearly, right? So if you take over here or here, so your constructed box is looking like this, right? Let me make a bolder marker. This, and this, and this. This is your box. But every value is not going into the box. Why? Because few values are disobeying the law. And these are the values what? And you can clearly see those values. And there are those values. Right? There are those values. When they get mapped, they will map over here. Right? So their functional value is here. So their functional value, if you see on y-axis, they are over here, right? So of course, these values are lying outside the interval. Which interval? L minus epsilon to L plus epsilon, right? They are lying over here. So limit does not exist in this case. Okay. So how are we going to use this idea into our current frame of work? Because we'll be dealing with the multivariable function. So when we'll be dealing with the multivariable function, basically we'll have two variables in the domain, right? So we shall have, because largely we'll be dealing with the two variable function. When the domain will have two variables, two inputs will be given to the function. So we shall have two variables in input. And of course, one for output. So roughly something like that. So basically this is your x-axis and this is your y-axis and this is your z-axis. So domain would be something like over here. So that means you'll be seeing the limit at this point of some function which would be of 3D shape, right? Let's say some sheet over here. So basically you are, again watching those values over here. Let's say your L is here and you will talk about L plus epsilon to L minus epsilon. Only difference is your domain is now become a region, a kind of, it may be a plate, it may be a disk, something like that. So here you are in two dimension. When you used to have in one dimension, when your domain was one dimensional, so you were restricted only to the two direction, either to the left hand direction or to the right hand direction of this point x is equal to a. So you cannot move in any other direction. But in case of two dimension, you are free to move in any direction. You can opt any path to approach this AB point. So that path may be a parabola, right? And that path may be a circular path, something like that. Right, and that path may be a straight line, right? So let me put it in different color. So when you are talking about AB, when you are in 2D, so you may approach this AB in any different path. It may be a straight line, right? So you may take a straight line to approach the point AB, right? Or it may be a circular path. It may be a parabola when you talk about this point, right? Or it may be a cubic curve, right? It may be a cubic curve when you approach this point, maybe a cubic curve or anything else, or maybe any different curve, right? So here you are not limited, you are not restricted to two directions. There are many directions, right? We'll be talking about this thing in the next lecture. And so basically the difference is when you were only talking about the left hand limit and right hand limit, here you are nowhere restricted to the left hand limit or the right hand limit, and earlier your domain was this kind of thing. When you say that this, you know, a minus delta to a plus delta, when it was an open interval. Normally it was an open interval, right? So from here to here, but now this open interval will get converted to a region, because we have a function whose domain is 2D, right? So we'll be having a kind of function where we say that f of xy is equal to z, right? So this AB, if you take any, you know, any region around it, so any, I'll not be talking more theoretically in this section. So you will have a kind of so many points in of 2 tuple around this point, right? So this is the basic difference. So earlier in your +2, you'll be talking about the left hand limit or right hand limit. Why? Because you have only 1D domain, right? So you can go in either in a back direction or in a forward direction, either in a left direction more precisely, or in a right direction to A, point A. But here you can choose any direction as your domain is of 2D, right? So that's it for